Okay, you're being recorded, just your warning that I'm obligated to give you. So here's a little snippet from A Gentle Introduction to Haskell. I think this is a really good resource online by these individuals, Paul Hudak, John Peterson, and Joseph Spassel. We're going to talk about actions and the way that they've defined actions. So actions are either atomic, as defined in system primitives, or a sequential composition of other actions. The I/O monad contains primitives which build composite actions, a process similar to joining in sequence using a semicolon. Thus, the monad serves as the glue which binds together actions in a program. Why am I telling you this? Well, the notion that there are like system primitives is important, because today we're going to talk about I/O, and I/O is something that like Haskell can't handle. Like that's an operating system imperative. Like so Haskell's going to have to ask the operating system to do stuff now, like grabs things from the user. Like there are other primitives that we've been using, like the data type for integer. When Haskell adds something together, we're not like, we could do it by defining this like data type for nat and defining addition in the piano way, like the way that you just did it on assignment 2. But in reality, Haskell's calling the hardware, right? It's asking the hardware to do the addition. Anything else would be crazy because that would be super inefficient to do any type of adding. So we talked about these monads, which were a way or a provision for us to reach inside of structure and get something. And today we're going to learn how these monads can be these atomic actions themselves. So like suppose we could like reach inside the action that's getting the I/O. So we're going to flesh this out over the course of the lecture, because it's a little bit of a mind bend. Okay, so last week we talked about the state monad, and this essentially enables or automates the process of like passing, like threading some shared data through a function. So let's just remind ourselves that a state transformer was some sort of function which, at its very fundamental basis, takes a state and returns a new state. We can also give this input and it can have output, but it's fundamentally something that can give you a new state given an old state. We also know that I/O is impure because of side effects. Like that was one of the first examples I ever showed you in class. Remember, we're talking in the first week that the output of a function has to be the same, because equal means equal. I was like really adamant about this. So if we had a function that said like took an integer from the user and then printed it, like that function can't be pure, right? Because the action of like what the human types on the keyboard is non-deterministic. So I said like I/O is going to be out of the question straight out of the gate for that reason. However, given now that we have these state transformers, how could we make I/O operations theoretically pure? It's a little bit of a mind bend. Everything. If we make I/O a state transformation over the state of your computer itself, or the state of like your computer and every other device that that your computer can talk to, or like taking this really to an extreme, like the status of every atom in the universe, right? This would theoretically be pure, right? Because you're like, because you could get the same. You're saying, given the state, like every bit on the computer is set to this, and then like the following thing is input, and then here's like the new state of the computer. That would we would have a state transformation which could read input. So I/O basically is a state transformation where the state transformation is on the entire world, the whole universe. So in fact, there is a data type for world, right? Everything. Who cares how it's defined? It's just everything. So I/O in this case is going to be a state transformer, which given the state of the world, returns an output and the new state of the whole world. So this is how we're sort of going to shoehorn I/O into being pure, by passing along the entire state of the world as a state transformation. So here are some basic I/O actions. So these are the two primitives that we're going to use. I can't really show you how they work, but we need to appreciate that given these two functions, that we basically get any I/O action that we want. So like, what are the two I/O actions that we need. We need to be able to read a single character, and we need to be able to like print a single character to the screen. So that is to say, we need to take, like, input a single character from the standard in and output a single character to standard out. Do these words resonate, standard in and standard out? Okay, so for those who this doesn't resonate with, sort of the Unix operating system has this philosophy that anything that it runs takes input and takes output. Now in Unix, you'd want to like tie things together with pipes, right? So that like you put input into like one program and it like outputs something, which you want to put into the next program, which outputs something. So that's why you have this thing called the pipe symbol. But then if you're passing stuff from like one program to another, you sort of have to agree on like a universal API of like what's going in and what's coming out. So like what's a sensible API to choose, right? So that everything has to talk with one another. Like what should the type going in and coming out be? Text, right? If you say all programs take input text and output text, right? You don't get to type it. It's just text. Thereby programs reading in text can convert that stuff. But that's the fundamental philosophy, is like an input pipe takes text and an output pipe outputs text, right? So because we're going to get these two functions, one for getting a character and one for putting a character, this now means that like compiled Haskell code can like sit in this pipeline, right? You can have Python code like write some data which goes into Haskell, which then like produces data which goes to, I don't know, MATLAB or something. So this really allows Haskell to join the party, right? In turn, because we haven't really done anything, we haven't like really built interactive APIs or like anything that could like even read data, which would be a huge problem. So let's just take a look at these things. So get character is going to be, it's like notice these things they don't take input or return output really. Like I'm saying get character is a function which is a state transformation over character. And what's the state transformation over? Well, the world. What's a put character? Well, a put character takes a character and produces an I/O action. Right, so I/O in this case is like the structure. You know how we're like always talking about structure and like functors were like a structure preserving operation. So we could wrap things in jest, we could wrap things in either, we could wrap things in dummy constructors. Those all qualify as structure. I/O here you have to think of as the structure. It's a state transformer. So this would be I/O, which sort of is a structure over nothing, which means, so what I/O action doesn't it make sense to like return anything? So what I/O actions do we have essentially? Read and print. One of those two doesn't make sense to have a return type. Which one? Print, right? Print doesn't have a return type. Print is an atomic action. So when you see things like this, I/O over nothing, like this is an empty tuple, is just printing. Right? That's the return type for when you just want to print something. So I'm surprised no one's like sort of raised this yet. Surely we can't pass around the entire state of the world to our functions, right? That's like, how do you even codify every atom in the world? And it's like, well, yes, of course we cannot do this. But in theory, if we could do it, then our functions would be pure. So in practice, we don't actually pass around the state, right? We just pretend that it's being passed around. And then theoretically, what we have is a pure function. Is everyone okay kind of with this like hand waving? What this is going to prevent us from doing, though, is like we can't ever pattern match out of I/O, right? Because we don't actually have the state of the world. Like so far, everything that we've been doing, like everything that we did last week, we could unpack, right, into regular sort of function calls, right? We could take our monad, we could reverse that to bind, we could like substitute the bind definitions and then the applicatives and then the functors, and eventually at the we would get some super complicated thing, but it was still like a pure function. But in order to do that, we needed to be able to pattern match out of the structure. Like when we're talking about the maybe data type, I needed to say this is what to do with over nothing and this is what to do over jest, right? Which means the structure actually, I could unpack the structure if I wanted. This is no longer going to be the case with I/O because we're not actually passing around the state of the world. There is no structure in which to unpack. So this is what this means. So it's tempting to bring to bear our previous knowledge of pattern matching to retrieve values encapsulated by I/O. After all, I/O is just a data type, right? So that means we should be able to pull apart the data type. Okay, so if we wanted to do pattern matching against the data type, this is what we would do. We'd say, give me info on maybe, and we'd say maybe A is nothing or it's jest of A. So thereby, this tells us how the pattern matching works. Everything in maybe A is going to look like nothing, or it's going to be something decorated with a jest. Okay, let's look at now info for I/O, right? In hopes to be able to figure out how to pattern match out of this. It's a system primitive. Right? That's why I talked about atomic actions at the beginning of class. So this is just saying, well, I'm kind of making a operating system call. We can't really pattern match out of this. I can't really tell you what I'm doing. I'm a system primitive, right? You can't. I'm like a kernel action. So don't ask. So this means we can't pattern match out of I/O because there is no explicit definition for its data. Okay, so if we cannot pattern match out of the I/O type, how can I manipulate data that's encapsulated by I/O? Yes. Exactly. We spent all last week and the weeks before devising and developing functions, applicatives, functors, and monads, which allowed us to reach inside structure and map it or do something to it without actually leaving the structure in itself. Right? So we can map over a maybe type, or we can fmap over a maybe type without actually, taking out the A and applying F to it. So we're going to use, if we can make this I/O type a monad, that means we're going to be able to use the do notation, applicatives, and functors in order to manipulate the stuff that's encapsulated by I/O. So it's we have an I/O action which we can jump into and then do stuff. But then we have to rewrap it in I/O, which should be something that we're used to at this point, because whenever we're working in a monad, the last thing we had to do is return, which means so that a monad action was usually extract something from inside structure, then do some transformations over that structure, do some transformations over the thing I pulled out of the structure, and then put the structure back on and give it back. We're going to do precisely the same thing with I/O. So I/O is a type in Haskell that is a monad, applicative, and functor. So we're just going to take that for granted, right? That the I/O state transformation is a monad, applicative, and functor. So we learned that these class instances provide functions that let us reach into structure in various ways. Okay, so there's one more thing I want to show you with monads. So there is this bind operator, but there's also this what's called an anonymous bind operator. So usually in bind, we usually have to say X goes to F binds to X, which goes to something, which Y goes to bind something. This is just going to be defined as this, right? Where there's we don't actually care to have a variable here. We just want to perform some action K, and this becomes relevant because we want to do things like print, right? And print doesn't have a return type, so that's when that monadic action is going to be relevant, right, for when we're printing. But it's just a little bit more syntactic sugar. I'll show you what it means in the do notation. Okay, so here again are our basic I/O actions. I can't show you how they're defined, right, because it's just C code essentially. So we can get a character and we can put a character. And when we get a character, this is going to return a state transformer. We're not actually going to get the character back. Or we can put a character. Only one of these two I can really show you output. So if I go here, I can say put a character A. Whoops. Oh, that's a string. Right, so I actually managed to like print A to the screen. That's why A doesn't have quotes around it, and that's why we sort of lost this new line. So the type of put character A is an IO action that prints, right? That IO action is printing, or the IO action can be like a sequence of IO actions, right? So that's how you have to interpret IO, as in like a brief sequence of IO actions. Like monads are also a provision for allowing us to sequence things. Like a lot of times in this class, I was saying you should be able to permute the input or permute the lines of a program without having an effect, with some exceptions. And working in a monad is one of those exceptions, right? So those binds were set up deliberately in order to help us sequence actions, right? We take X to something, which takes Y to something, which takes Z to something. That's a way to sequence a set of actions using a function. A safe function of the following type does not exist. So you're never going to be able to get a function, foo, which goes from IO of A to A. Why can't we do this? Or why is this unsafe? Is it pure?
It's the thing about not having the world or whatever.
Well, it's kind of like, so this function has to return the same thing every time we call it in order to be referentially transparent and pure, correct? Okay, but the first thing this function does is ask for a character, or it does an IO action. Let's suppose that it takes a character from the user. Is this always going to return the same thing? No. So there is, if you look deep enough in the documentation of Haskell, there is something like called unsafe getchar. There are some instances when you're absolutely certain that an IO action is never going to change that you can use this. Like, you know, what's the architecture of the system I'm compiling on? That would sort of be safe to bring in as a constant or something like that. But we are never, sort of in your usage, you're never going to be able to unwrap the IO wrapper. It's just, you're obligated to interact with IO through its monad. Okay, so recall that main is a special function whose type is presumed to be IO. Loading the following into Haskell will throw a typing error. Why will this throw a typing error?
Double quote, single quote.
Oh. Well, that's not going to throw a typing error. That's going to throw a syntax error, I think. Okay, so let me try to correct that. Okay, so here's a fresh file. If I say main is equal to A, why is this going to throw a typing error? Well, yeah, like the type of main is presumed. Whoops. Maybe I cannot. Like main is of type IO, right? So when I said main is equal to A, that's not IO. That's not an IO action. That's a character. How can I put the IO wrapper on this?
Just write IO.
I wouldn't write maybe if we're working in the maybe data type.
If you say put char.
Return. What? Is it pure? I thought return should have worked, I thought. Oh, I need to be in a do. Do return A. That should work. What the shit? I don't, well, pure A shouldn't, okay, so that's weird. I would have expected that to work. Well, in any case, yeah, like put char is going to work. That's kind of disappointing. Oh, yes. So this would have to be IO of char. Okay. This is where sort of things get confusing because I don't actually want to encapsulate a character. Like I want to convert this into like an action. So I'm just going to leave it as put char. But that's disappointing that wouldn't work. Okay, so I bring this in and it says I can't do this because like I want to be type IO and that's a character. So Yeah, how come I said that it works here? I'm going to try this again. Yeah, maybe if I just delete my main. Return A. Oops. Oh, okay, that works. Okay. I let it infer the type. But I don't know why the type was an IO of just IO. I'll follow up after class. Huh? What's type of main? Oh, it is IO char. No, but that's returning a char. That's a little bit different than what I was trying to do. Okay, let's just keep going. Because that's actually returning something. Like this is returning, like this is encapsulating A in an IO, which is different than what I'm trying to do. I'm trying to like print A. Okay, so we'll do more examples and this will become more clear as we move forward. The IO monad is kind of weird. Okay, so what have I done? Foo, main, let's just go to the next one. Okay, this one will be more informative. Write a function put string that outputs a string rather than just a character. Okay, so we had put char. I'm just gonna put this here so we can use it, or just refer to its type. And I want to put a string. So string is going to take list of char or string. And like because I just want to print it, like the IO is not going to encapsulate a type. It's just going to perform an action, right? So that action is of type sort of empty. That's it. I know this is sort of tricky, but you can just interpret IO of empty as being like what this is going to do is print something, right? That's the action that I'm going to perform. Okay, so what should I do? Well, certainly we need to do something for the empty string. Can I do that? Maybe I'll just do this. So what should I do in the case of the empty string? Yeah, put the empty string there. Like print empty. We'll do print string line after this. But well, okay, sure. We could do this now if you wanted. Okay, so we'll jump no, let's do it. Let's stick to plan or things go bad. Like I lose control of my keyboard. What is happening? No, I've been having... Oh, wait. Okay, no, I'm back. Jeez, that was weird. Yeah, let's just put a character. We'll put nothing. Sorry, I'm losing that just threw me. Just let me check. Yes, sorry. Here I want to return the empty action. I'm in the IO monad now. Okay, so what should I do? What action should I perform on the empty string? Well, I need to perform the empty IO action. Does that make sense? Okay, we'll try the recursive one. Put string x con x is. So we're going to use the monad do. And then I want to put char x. And then what do I want to do? Put string. Is this going to work? Typo on line 6. Other string, yeah. And actually, I'm going to have to add the. It's not my day, guys. I'm going to have to do this because it's defined in the prelude. So is this going to work, or are we going to get a typing error?
How will this return?
Hmm?
How will this action? Sorry, what do you need to return? Sorry, my bad.
It's returning an IO sequence.
Which is put string.
Well, put char is going to return an IO sequence, and put string is going to return an IO sequence.
So
I don't know. So what do you think if I hit enter? Yay or nay?
yay.
Okay, so let's try it. All right, so you know it's like we printed something. But it's kind of weird, right? So let's go over this again. What action do I perform when printing the empty string? Well, I perform the empty IO sequence, right? There is no IO to print the empty string, by which I mean the string of length 0, not space, right? Space is the thing I tried to print, which screwed everything up. Okay, so I'm saying putting a string, right? Xcon X means do put a character, and character is like a single IO action, right? So this is one sequenced IO action to put a character, and then do the sequence of IO actions.
If you didn't give it a type definition,
It would infer it.
it would infer.
Yeah, because it infers it from here, right?
Oh. So you can just use the monad return.
Well, we don't need to put return, right? Because we haven't pulled anything out of structure yet. And in fact, there's nothing to pull out because it's an empty IO sequence, right? In terms of the base, like what we'd be pulling out would be like prints, would be things without a return type. So like it's sort of weird because like the thing that we're encapsulating is nothing, right? Nothing is being wrapped. We're just performing a sequence of actions. Because like what should a function that prints returns? That doesn't really make any sense. Like we're basically now talking about procedures. And like the notion of a procedure like makes no sense in functional programming because a procedure isn't a function, right? It's a procedure is like intensive, like really much an imperative idea. If a procedure is basically just a list of actions, like do the following actions. And I'm saying IO, the state transformers sort of help us perform like sequences of actions when they're done in monads. And in particular, the IO monad is going to allow us to sequence IO operations, like IO primitives. The more examples we'll do, the more clear this will become. But like I acknowledge that the IO monad is like extremely strange, which is why we're in week 10 and still haven't done Hello World. Right? This is going to be the first programming class where Hello World was like the last thing that we were able to accomplish. And it is in the class. Like, well, let's do it now. Let's write a function that returns Hello World. And there's still stuff that we can terminal. Like, okay, so here's foo. What should the return type, like, so I want to have foo, and I want it to print hello world. And let's just do the thing you wanted to do. I'm just going to call this put string line. And instead of doing an empty action at the end, we will just put the character new line. Okay, so let me just compile that to make sure it reads in. Cool. Okay, so if I want foo, and like, how now do I write a hello world procedure? Right, so foo is going to take no input, but what's it going to return? IO action of anything or something in here? String? No, right? Because it's just performing a print, right? So you can interpret this as print. So what do I say here?
Put string line of hello world.
Wasn't that satisfying? It only took 10 weeks for us to get here. But like now you understand how like this is actually occurring in a like referentially transparent way. Because if you give me the position of every bit on this computer and perform the exact same IO actions, I am going to indeed perform the exact same output. Right? If you're like saying, like, read from this file and ensure like you have a function that counts the lines and counts the number of lines in a file. Okay, how can I make that pure? Well, I'm saying, well, you need to tell me like, so I'm going to have a function which is going to call that file, but also I need to know like the whole state of the computer, which contains like the file contents itself, right? So if you give me that same file with the same contents, then I'm going to give you the same output. And you sort of see it like that way. It's really hard. It's like tricky to grapple with, but if you think about it, it's like, yes, if you do indeed give me like, tell me all the information in the world, I can perform the exact same IO actions and guarantee you I'm going to give you the same results. Because it's not like saying, tell me how many lines are in an arbitrary file. It's like, tell me how many lines are in this exact file with the exact same like lines in memory, right? So you're always going to get the same thing back. Okay, so there's our put string. There's put string length. There's our foo. Oh, okay, so just notice, like, we could have, like, output Like the REPL itself is doing IO actions. Like we've been working with IO the whole time. So clearly it was having a way to like read stuff from us and print stuff. But notice like when we set bar equal to the string hello world and just like have its string representation echo to the screen, it includes quotation marks. It's like we have indeed accomplished like printing to the screen rather than just showing the string representation of this string. Write a function trip print that inputs a character and then prints the character out 3 times. Okay, so let's go back here. This time we're going to need getChar. And then we'll just use the system primitives for those. I'll just remove them. We don't need this either. So we have putChar, getChar, put string line. Okay. So we want to define something called trip print. And what's trip prints? So we need to input something from the user and then print it 3 times. So what should the function type be? Let's think about this, right? So like what are we doing, right? We can't really, like what does it mean to take a char from the user? What is that? It's an IO action. Okay, and then what does it mean to like print that 3 times? What's that? It's an IO action. So like we've just done a sequence of IO actions, haven't we? So what's the return type? Well, it's a sequence of IO actions.
Is it not a function from IO to IO then?
No. Because you don't want to return a sequence of IO. Like you don't want to, what does it mean to take a sequence of IO actions as input? Like this IO is a state transformer, right? So it's something, it's something that you can like get new structure from, but yeah, it doesn't really make sense to move from IO to IO, right? So this is just going to be like a sequence of actions, one sequence of IO actions. So what do I want to do in this sequence? Well, I want to do, right, I'm in the monad, so what's the first thing that I want? I want to get a char, but what's the type of get char? Right, so it's an IO structure wrapping char, but I need that character that it's wrapping. How do I get it? How do I reach inside get char and grab the char? Using the monad. That's exactly what this means, right? Reach inside getChar, that IO, right? It's wrapping something. Grab the character that it's wrapping and pull it out for use here. I'm allowed to use it in the monad only. I wouldn't be able to do this outside of, like, you understand I'm in an IO monad when doing this. Like so I'm allowed to use the sequenced IO actions while doing sequenced IO actions. So I'm saying, okay, getChar, this is go get a character from the user. That returns a state transformation of IO over char. I'm going to reach into it to grab the char. Now how do I print it 3 times? That would work, but what's a better way? Well, we don't forget, like we have these, right? Oh, okay, so I think there's also put string, which is just string to IO. Yeah, so let's just do that. Put string, and then XXX, right? Don't forget, like, strings are just syntactic sugar for character lists, so that should be a character list. Okay, so can someone predict the behavior, then, of what's going to happen here? If I press trip print, what's going to happen? We should always predict behavior. What do you mean? No, that this will be fine. Well, let's walk through these sequenced actions. I'm going to hit trip print. It's going to enter that monad, and the first thing it's going to do is get a character, which means we're waiting around, right? Where there's now some type of lock made where we're waiting. Do I have to hit enter or anything like that? No, yeah, we won't have to press enter. It's a IO action that waits for any character to be pressed, right? Like A enter would be 2 characters, technically. So the behavior here is if I press K, it's done, right? It's read the character from the user and it triple prints it out. That first K there is the K that I typed. It wasn't one that was output. Right, so the get character really is just a saying, yeah, get the next thing that the user types, grab it, right, and encapsulate that in IO. Yeah.
So if we were given this question on an exam and our result printed out 4 Ks, but it asked for 3.
No, one of the Ks wasn't printed by your function. One of the Ks was printed by the REPL. Right.
Okay.
So I would accept either, right? Or I'd make it very clear, like, what the output should... Like, I always give you usage, right? So you would see this in the usage anyways. Okay. Yeah. But that kind of stuff I'm not going to ding, right? At this level, you're allowed to make sort of like if you could do it 4 times, you can, like, to correct it, you just have to remove or add 1x from that list, right? That's a very menial change, right? You've more or less demonstrated that you understood everything else, right? So I wouldn't deduct for something like that. Yeah.
What if you want to copy paste into the REPL? Then would it get the first character from the copy paste?
If I copy paste it, okay, I'll copy paste trip print, and then I'm gonna paste now, okay? What did it do? No, we have to, yeah, so I copied trip, okay, so I pasted trip print.
And it's taken the first one? Well, if we test with something that isn't...
No, okay, yeah, those are the 3 T's.
It could be this first or the last.
Yeah, if we test with like trip print.
Sure, well, I'll just do this. A, B, C, right? Okay. Yeah, it depends, like, how, like, we have to sort of think about how copy works, right? And how pasting works, and like how it's actually being, like, I don't know how it gets, I don't know much about the operating system level, but I think when we're pasting, yeah, like the first thing that was pasted was A, but I don't understand why the whole string gets printed when I paste it. That may be like, I don't know.
It needs to do that calculation before it prints out.
Yeah, maybe a scheduling thing is what I was going to say. But yeah, now we're getting pretty into the weeds. Yes.
So I think what this gentleman was asking about expecting it to need an input of the IO state. So the reason it doesn't, because it's lazily evaluated, so it returns IO without actually having done any of those actions, and then the function above main then actually executes them by doing the state transformation on IO.
Yeah, that's correct, right? So these IO actions are delayed like the rest of the system.
Because even in C, there's a function above main. Main
Right.
isn't actually the first function.
Right. Okay. So
This is the same.
more than likely, but that's outside of, like, I don't know, so I don't want to really talk about it. But that seems sensible. Yeah, I don't know much about like how the compiler here works or what's happening behind the scenes. In fact, I'm not even really that concerned with you guys interacting with I/O that much. I just wanted to show you how it works and like because not being able to read files is a big problem, I would say, in Haskell. Like, I can maybe make some argument to say I don't really care about talking to the user, right? I can still do like scientific computation and research with Haskell without ever doing user interactions, but I'm going to need to read from files at some point, right? So we should really insist that we can read from files, which is I/O, but like in a more safe type of environment. Because when you're reading from a file, you can assume the file is well formed, or you don't read it. So file I/O is what comes after here. So anyways, trip print, that's how that works. Write a function getLine that reads a string of characters terminated by the new line character. Okay, that would be the more traditional way of entering input. So what did I call this? GetLine. Is this in the? Right, it's there. So I have to do a custom one. Get line prime. Okay. So what does it mean to get a line from the user? Yeah.
You keep taking input and basically will keep asking you for input until
Right, but what's its type? Like, what's the type of get line? Yeah, it's IO over string. Like, because this time I want the IO action to like actually give me something. Right, so remember, IO is like the structure that we can put around stuff. When printing, there's like nothing to do, right? It's like the IO action is not really like obtaining anything. In the case of, where was it? Get char, right? Get char was an IO action that ends up encapsulating one character. So to get a line, to get like many chars, would be an IO action that sort of encapsulates a string. Right? So it's like if we want to do anything to do with IO, we have to like jump inside the IO structure, do what we need to do in the IO structure, and then put it back. But then we have to talk about what's inside the box of IO structure. So inside the get char IO box is a single character. And in order to use that single character, I have to jump into the box. And I can do things to it. Like I can say, count, like tell me what the ordinal of this character is, and change it to an integer. And then we can have something that says, that takes an IO char to an IO int. But so this is just going to be IO of a string. So how do I get this now to like read a string? So I think what you said is the most appropriate. So I want to get a char. That's going to be pulled out with x. Okay, so now what do I want to do?
it's kind of like if x is the new line.
Yeah, so now we do get to use an if expression. Well, we shouldn't be surprised that like imperative structures are now reappearing now that we've like simulated this. But this is okay. Like we're allowed to use if expressions when like branching on two things. So like here I'm just going to say if x is this new line character, then we'll do something else. We'll do something else. So what should we do in the case of a new line character?
Stop, like return x. Oh, no,
We need a list
list
of
of x.
characters to return, right?
Well, no, like suppose like this is the base case now, right? So we've like, yeah, well, not what nothing. Like there's a lot of nothings. Empty string, right? I can't do empty. Oh no, empty string. Yeah, I have to be careful with what quotations I'm using. Thank you. Right. So if like we just hit enter, then the string that like I'm holding then is the empty string. Otherwise, what am I doing?
You're concatenating x to the function called.
Right. So we have to be careful about this. So you say you want to eventually return like x concatenated with like the rest, right? But then what's x is?
It's also get, essentially get line.
Yeah, we recurse. X is get line. Like get the line. Whatever's like, we already read one character and now go get the next one, right?
Yeah. Question though.
Yeah.
So this will. I just don't understand the looping. How will it loop? And how does this work? I get that get.
Okay, let me get it to run first. What did I do? I may have my brackets off. Oh, yes, that's what I did. Yeah, because like this is a different IO action. Yeah. Well, because this one here, so here when we're pulling out, this means we're in the IO char monad, right? But here, this is like in IO string monad. Right, so that's why I needed another do, right?
We might need to return a single character though in line 11.
Line 11. No, we're returning the empty character. We're returning the empty string.
But you said we're in IO char monad, so if we're returning an empty string in IO char.
Oh, sorry, did I put my do in the wrong place? Yeah, you're right.
Yeah.
Yes, I put my do. No, that should be fine. No, that should be fine. Because eventually, like, I'm returning to this monad, right? Like, when I'm pulling, I'm in the IO char monad, right? But then like my return has to be for the return type of like the thing I'm defining. Okay, so let's just make sure that this is like working, and then we can go through it. Get line. Hello. Not very impressive, right? But what I can do here is say x. Oh no, yeah. Like what this is basically is like get line hello is now like a state transformation, which we can like map over. Right? This didn't actually like return anything. Right? Don't let this confuse you. Right? So what we have now is sort of a state transformer over I/O that allows us to like get a line from the user, and we'll use it. I'll show you in its usage. But back to your question about how this works. So what was your particular? You don't understand how it loops?
How's it looping? So x does get line.
Okay, so yeah, x gets the character, gets one character from the buffer, from the input buffer. And then it asks if that character is a new line. And then if it is, it just returns like the empty. Oh no, am I missing? Oh no, that's fine. Yeah. And if what we pulled ended up being the new line, then the string that we're currently holding is the empty string. Right?
So is the return in the if?
It's for IO string.
That's for IO
Yeah.
string.
Right, because these have to, like both if expressions have to return the same type.
The problem I'm having was with the first return on line 11. Like, will that not return out and get out?
No, oh, so return doesn't end anything. Okay, let me do this instead. Yeah. I actually have a slide about this. Right? Like return is not like return in the imperative language where like something ends. Right? It's just saying like apply the structure onto this. Maybe we'll do more examples. Like the more examples we do, the more this will make sense. But yeah, working with the IO monad can get kind of strange. Okay, let's do a different one. Let's do. Okay. So here are some useful string functions. So there's two functions, show and read. So show takes anything that's showable and like converts it to a string. And read takes anything that's readable and converts it back. You just sort of have to like tell it like what you want it to convert to. You could be clever with these reads. If you like read something inside an expression, the type can get inferred. So it's going to complain if you say like read 2, but it shouldn't complain if I say read 2 plus 2. Yeah, because in the latter one it can infer that like 2 needs to be a number, and in the former it can't. Yes?
Is read limited to like primitives, or can it?
It can read anything that's anything of an instance of a readable type. I don't. What kind of functions?
Is that like an eval?
I don't think so. Like it's basically like the first thing it has to have is a string representation, and that string representation has to be like a unique constructible element of that set. Like there should only be one way to ever write something, so we could read it back. It needs to be parsable, essentially. I don't know if that answers your question. Can it read Haskell code and get a function? Yeah, but that would be a parser. Oh, you want to know if this read will work. Oh, okay, let's see. I doubt it. I wouldn't even. I'll give it a try. You can experiment, put it on the ed stem. Sorry, you have a question? Yeah.
Yeah, can we just get Haskell to derive read for a new data type we define?
Yeah, you can always write instances of read for any custom data types that you want. And that's essentially what your assignment 3 is. Derive what?
Type derive read the same way you can derive show.
No. Because like that's not deriving show. There was sort of like a default way of showing anything because it just spit out what the data representation was. The opposite of that doesn't make. There's no generic way of reading data into like a structure. There was one more question. Yes. Oh, okay. I think that's just stretching. Okay, so let's move on. Write a function string length that prompts the user for a string terminated with a new line and then prints the string's length. Okay, so now we're starting to actually like learn how to like take stuff and do transformations on it. So we want to do string length. So I'm just going to keep adding these here, because what we're doing is just repeating repeating stuff that are in the prelude anyways. So this get line is just going to be IO actions over string, and this is terminated by new line. Let me just confirm that. Whoops. Get line. Okay, perfect. So get line and get line prime are doing the exact same thing. So we want to do string length, and this should read string terminated by new line and prints string length. Okay, what is the data type, or what is the function type for this?
I think, is it int IO to int, returning int?
You can never return something. You can never take the IO wrapper off.
So it's IO int.
That's correct. IO int, right, is what we're going to be able to return. Oh, no, that's not right. Well, I'm saying print the string, right?
Oh,
Right.
not return the string length. Okay. 'Cause that would
Not return the string length, because the best we could do is return an integer encapsulated by IO. Right? So I'm making it a little bit simpler and saying let's just print it to the screen. Let's think of the things that we have to do here. So what do we have to do? Get a string from the user and then print it. So those are two sequenced IO actions. Do we end up encapsulating anything? No. So what is the type here? It's just a sequence of IO actions. So again, if like the last thing that you're doing is a print, then you always are going to be IO of empty.
So would it be correct to say you can't really have I or something to I or something in a function?
No, we can, and we because like if I give you two IO actions, like suppose like one was for like reading an integer, and like another one read a string, and I could create like a new IO structure over that. Like they could be inputs to stuff, and I can reach into both of them in some limited, as long as the typing works out. Just treat them like you would treat any other structure. Like we can have a function that takes two maybes, or we can have a function that takes two eithers, and then work within their monad. Yeah. Okay, so how do I program this? Yeah, so I always want to be in the monad for sure. So we want to get line. That's going to get a string terminated by a new line. Then we want to like pop it out. Huh? Yeah, that's what we want, right? Where?
I mean, could we
We can't sequence actions like that though.
could we go through everything in X and then basically return 1 plus check the length until it's new line, so get an if statement, kind of like what we did with get line?
Maybe, but let's think about like all of these structure preserving operations that we've been using. So what is get line? Like get line is going to be an IO wrapper over string. Is there any way that I can reach into this IO wrapper and change this to int?
Oh yeah, you can use fmap.
I can use map. What should I map?
Length.
Length. So now what's inside this? It's an IO wrapper over an integer. And that integer happens to be the length of... I did one transformation, right? I had IO of string. So I had an IO container holding some string that was input by the user. And I'm saying fmap, like map over that string input by the user length and change it to a number. So then pull that out. So when I pull it out, x is what?
X is int.
X is int. So now how do I print it?
Question, will this take the new line into it?
No, get line eliminates the new line. Yeah.
Put string line. Okay. Probably
Put string line x
you need it on the do.
to what?
I don't know. I just feel like you might.
Well, there is a mistake here. What am I trying to? What does put string line need to take? And what are we giving it? So how do I fix that?
Can you just do put char?
I think it's show. Show takes anything from the showable instance and like converts it to a string. So this is what we want in this case. Okay, so let's see if this works. String length, enter. Blur. I assume that's correct, or off by one at most. Yeah.
Could we make it sort of like string length, and then you're allowed to put input as arguments into the function, and then calculates rather than having it on a separate terminated line?
What do you mean? You want to put like an extra argument here?
Is that I'm just
Like you want to put like an int maybe?
No, well, I'm just saying like perhaps in imperative programming that we do like length of, and then we write the string. Never mind. It's okay. It's okay.
Okay.
I don't know what I'm saying.
Sure. Hold on. Yes, sir.
Doesn't fmap preserve the structure? So isn't x IO int?
Yeah, X is, but we're using the monad to like pull it out with the arrow, right?
Oh, so it doesn't stay.
No, that's what the arrow is for. It allows you to like reach into the structure, pull out the thing, use it, but then you got to put it back. If that makes sense.
Where is it put back?
Here.
Oh, but it puts it back as a string again.
No, put string length will return an IO action.
Yeah.
So this is in fact like this is returning that. Right, so that's the line sort of which is like putting it back, putting the structure back.
But the one you took it out of was the
Was IO of the thing I took it out of was IO of string. Then I turned it to an int.
or takes it out.
Yeah, I go into the box, I apply the map, then I pull it out, then I like put the empty wrapper over it, right? Because it gets printed. Like I'm changing it to an action instead of being a value, right? So we can have IO actions which encapsulate values, or IO actions that just perform actions like this print, in which case the wrapper is going to have it's going to contain nothing, right? This is sort of what we say when we're like wanting to wrap a print, essentially. But I know it's a little bit tricky, this IO monad. Yes.
If you want the function to like give you back the length without printing it, how would you do?
We can't hand back the length. The best I can do is hand back the length encapsulated in an IO action. Like this would be the best I can do for you.
So that would be return X?
If you just wanted to return that
Yeah, without printing.
without printing, then I would just do that essentially. That should work, hopefully. Now it's always, I have to make sure, because somehow working with length, the typer, it needs to be an int. Okay, let's see if this works. Yeah. But it's not, I can't really show you what this does, right? Like this, that's not really printing anything. That's just, but like, so if you call it, like you sort of get the integer, but I'm saying it's in the IO action. Like this is good though. So you understand what's happening? Like the fact that we can't ever remove the IO wrapper means that in our code, there is like a visible delineation between things that are like really pure and this like sort of simulated purity that we have. Like once you make this simulated purity, you're stuck. Like I'm saying, you can work with IO, but you're never allowed to take off this IO wrapper ever, which sort of like theoretically gives us the purity that we need. Yeah.
If you go back a bit and you instead of
In slides?
no, in like Control Z,
Oh.
instead of put string line, you just had return show X, just wrapping it in IO. Does that also just go and stand it out?
I don't think that's correct. The return here is working kind of bizarrely. There's like another thing for print. I'll have to get back to you on that. What return is doing in an IO wrapper? Because you would expect that it would just put the IO.
Would IO
Because putting, like, the return would just put the wrapper back on, but I'm actually doing more than that. Like, I'm actually saying perform the IO action of printing and then wrap that. Right? So I'm not sure I'd just be able to say, like, just put the IO wrapper on this without, because like the puts string length is doing two things. Converting the show to an IO action of printing and then wrapping it, if that sort of makes sense.
Yeah.
Right.
If you put the return on the show X, I guess it would do what Miri's thing did before, where it just returned an IO element. Because you're taking it out of the box. And then
Yeah, that should return, yeah, IO string. Right, yeah, but it wouldn't print anything. Yeah. Was there another question? Let's just keep doing more examples because like this is really where we figure there's an alternate way of doing it. Write a function addio that takes an arbitrary number of integers separated by space and terminated by a new line, which then prints the sum of those integers. So again, prints. Okay, so let's do this one together. Addio, what's its type? So I need to take a bunch of numbers separated by spaces, and then I gotta print their sum. IO blank. Yeah, now we're getting it. Okay, so now what does addio have to do?
Get line.
Well, certainly we're gonna have to get a line.
In order to reach.
Well, yeah, we can reach into it if we want.
we wouldn't have the sum.
So far x's is like, this is what x's looks like. X's is going to look like this, maybe. Right?
We want to split it based on spaces.
Right, so there's this neat thing called words, right, which takes a string separated by spaces and does that.
And then after
Well, I guess it would be better if I just showed you that it worked like this. Okay, so let's map this words. Let's do it. Okay, so now inside this get line is a list of string. Oh, wads, words. Now what?
also map, what's it called, to integer or something.
Yeah, we have to read, but we have to do this carefully because I needed to let it infer. Okay, so here I'd want to do something like x is equal to, or I want the list read x as an integer such that x is drawn from x's. Okay, but I'm not allowed to I can't just write a statement like this. So here I can do something like let y's equal to this. That's fine in a monad. Right? This wouldn't work. This is fine. Right? So in a monad, you have to say let when you want to like spin up a variable. Okay, so that should give us a list of integers. And then what do I want to do in the end?
Print the sum of that.
Okay, well I can get the sum. Right, there's the sum. And you want to print this? How do I print this? Show it, yeah.
And then put string.
Put string line, I guess.
Yeah. Spelling capital.
Oh, is it like this? Yes. I think that should work. No, maybe I need a dollar sign. Okay. So addio, 16, 17, 18, 91. 142, boom, right? Look at all of this like super sophisticated programming we're doing now. Yeah.
There is also, I think, because you use the functor words and then get line, you can also then apply that to read, just there, in that one call.
Yeah, but I somehow have difficulty like mapping the read somehow. I'll give it a go, but I had some difficulty with this last night. Okay, so I'll try to map this to this. But what I need to map is what? Lambda x to read x as an int. Somehow that wasn't working for me. And then it would be this, yeah? Oh, 2 colons. Maybe that was the problem. No, it's
What I was saying is there is a function that can just, they don't need a functor, because that thing is, sorry, you do need a functor, that thing is a list of string of numbers, but it takes that list of string of numbers and converts it into essentially that. So you don't need x, it's just read of x.
like I could redefine, we could make another definition for words, like that returned integers rather than words, or strings, yeah.
I think it might be a problem because you have to like.
Yeah, no, you're reaching into the IO structure and then like need to reach in like another structure. So that's why I sort of separate. I'm sure it's doable, but
Yeah, you could just like use map and then.
yeah, like the lambda expression would have to itself be like be doing a map. At which case it's like we're just making it way too complex. Like this is obviously working, it's readable, it's my preference. But yeah, we could change words so that the return type of words was were integers rather than strings. That would work as well. Yeah, obviously there's like a bunch of different ways. But like this is sort of working, this is how you work with IO. Like this is how you work with monads. So you can still use all of the other pure functions that you've defined after you've pulled something out of its monad wrapper. So that's sort of like what we're doing here, right? We're saying we're either like mapping into or once we pull out of using all of our pure functions. So it's still sort of, you can still stay in the functional paradigm. Here's an example about this return not returning the way that you would expect it to. This would also work. So this is kind of weird because I'm just like putting a wrapper on something and then pulling it out of the wrapper. Right? This.
That's the let statement. That's a substitute for the let statement.
Yeah, this is a substitute for the let statement, but it's sort of silly to like wrap something and then immediately pull it out of its wrapper, but it would work. And it's just to emphasize the fact that this return isn't ending computation. It's like putting structure back on something. So like this wouldn't escape, right? So that's why they're going to change return to pure, I think. It's just too confusing to have it as to use do and return in the same place. Just makes it look too much like the imperative one.
Can you have pure and return equal different things?
No.
No.
They both have the same type. They both are supposed to do the exact same thing. So,
Alright.
and they,
It's weird they ever introduced that.
well, that's why they're going to remove it. Like I think it also defaults to pure if you don't include it. And you also have to be an applicative. Maybe there's cases where you could do it differently, but I don't know. Like most of the time it's just pure and it will be default by that. What's this one? Right. Okay. So we've been using the same pattern over and over again today. So I'm giving something which is an integer and I want to convert it to a string and then put string it. So there's actually something called print. Right? And print is just literally the composition of show and put string line. And so I prefer put string line show because it sort of keeps me in the functional paradigm, but many other people use print. So, but you just have to be careful because you can only use prints like in an IO monad. Right? So just be careful about that. Okay.
Is there a call? Sorry.
Where?
Oh, yeah. Okay.
Oh, this one? Yeah, it's composition.
Somehow looks like attribute or something.
Yeah, I can get that. Okay, so let's just keep forging forward. Where's my other slides? My screen sharing is paused. Why? No, that's not the right one. I want 19. Now what? Oh, file IO. Yeah, that's what I want. Okay, so now we want to talk about not like reading in stuff that's been typed. That's what I sort of care about that less. What I'm actually interested now is like how do we get Haskell to read from files? Now, I was kind of fibbing from before. Like these getLine and getChar aren't necessarily taking things from the keyboard. getLine and getChar were reading things from standard in. So the standard in is just like an input pipe which says here's a stream of characters, and the stream of characters is coming from some source, but like it doesn't matter what the source is. It could be some human typing, it could be some like network communication, or it could be some like reading from a file. And it's that reading from a file that I want to focus on right now. But essentially everything that we did previously is going to be at play here, because we just have to abstract away the keyboard and change that to the standard input pipe. So here is a program that's going to do what? You tell me.
The same function that we wrote.
Good. You guys are on top of it. So what I can do to this now is compile it, which is the first time we've ever compiled Haskell code. And I want to compile it so I can use it in this Unix pipeline that I was talking about. So you can create these executables in Unix, and each of them are going to have an input pipe and an output pipe. And I can put these things beside one another. So now that I'm going to show you how to compile this, this means that you can include Haskell code in these like Unix pipelines. So all I did was change the definition of ADIO to main. So that's when you compile something, that's what the standard input is going to be pointing at, is the main function. So let's just do this. Okay, so I'm just going to delete everything. This we're going to change to main. So we're going to change to main. What is this called? Foo. So it's now GHC with no I, because we don't want to enter the interactive mode. I want this to generate. Oh, sorry, chat. Oh, sorry, chat. I don't know what's up with these technical difficulties. How about now? Okay, perfect. Sorry about that. Poor chat. Okay, chat. So like I just copied, pasted, like this is the ADIO function. I just changed it to main. And so you can see that we have access to foo here. Or is it not there? Yeah, it's here, right there. Okay, so what I'm going to do is I'm going to say GHC. So I'm going to compile this. I want an output file. Let's call it ADIO. And the thing I wanted to compile is foo. So this is where all the power from Haskell comes from. If you take some of the code that was like bad, that was written for assignment 2, it may not be bad once it's compiled, right? Because Haskell can play a lot of compiler optimization tricks. But now that I have this ADIO routine, I can actually do this. Call it like that. Whoops. Oh, I can backspace. 7. All right. Or I can say, here's ADIO, take as input this string. Oh, this may not work. No, I have to. Okay, let me just spin up a file. Yeah, touch numbers. There's a way to do it. I'm just not that great with. Oh, echo? Is it here? Did I do it? Right. Okay, so I want to echo this, and then give it to ADIO. I have to execute it. Oh, okay. So there's a great example of like using Haskell code in the Unix pipeline, but I'll just show you another way. So just let me get these numbers .dat. 1 1 1 2 2 2 5 5. Enter. Okay. So like I should be able now to say to ADIO along its input pipe, give it numbers. Oh, I've been reading too much. There we go, 19. Okay, so it doesn't, like, the fact that we were using getLine here, this wasn't, like, strictly speaking, an imperative to get anything from the keyboard. It was just get the next character from the input pipe, right? And we can have several, we can, like, have the input pipe pointing from anywhere, essentially, anything that can pass out standard in. Like, in fact, I can even say, like, this itself, like, outputs its answer. And there it is, right? So we can always like read stuff out and push stuff out. Yeah.
Is the GHC compiler converted into essentially, so it's binary, right?
Well, yeah, like everything, it basically gets you C code, and then that C code is compiled, and then you can run it, right?
Fair enough. So I guess you could kind of go back into C with that.
Yeah, like everything that we've written in Haskell essentially becomes C code in the end, which becomes assembly, which becomes binary. But yeah, that's just like that's how we build programming languages. They all write to the one underneath them, essentially. It's because like the computer itself isn't one built for functional programming. Like this one is built on a von Neumann architecture. It's like purpose built for doing imperative programming. Like, so we're going to have to do some of these conversions. Like we could build a different architecture of computer, which is like purpose built for functional programming, but I don't know if one like that exists or not. But yeah, everything gets put to C. Python just went through a bunch. I think Python 3.10, they're really like cheering that it's going to be way faster because of optimizations that they've made. But you'd be surprised how fast your code can run once you let it compile, like rather than letting it into its interactive mode. You're going to use like a fraction of the memory. What about interactive file I/O? Or what about multiple files, right? So what I've shown you is just really good if you want to like pass one pipe in and one thing out. Like what happens if I want to read from like multiple files and like write to multiple files? Then this like piping is not good enough. So I just have to show you one more thing. But there's one more thing I need to show you, and it's the first time in this course where we've had to import something, right? We have to leave the prelude, which is kind of sad. So we're going to have to import system.io, right, to get all the things that we need to work with files. So you should be, I'm sure all of you have opened files before and familiar with terminology like file handlers and file pointers. Okay, so there is a data type in system.io for handles, for file handles, and closing them. So if we import system.io, we're going to get the following things. We're going to get a data type for handle, which is abstracted, system primitive. It's going to define a type synonym for file path. It's going to be just a string, as we would normally expect, right? An absolute file path or a relative file path. We have some modes for reading files or for working with handles. The handle could be in read mode or write mode or append mode or read-write mode. And then we can open a file. To open a file means to give me a file path, to give me an I/O mode, and then I'm going to give you back a handle, but that handle's wrapped in I/O, right, in the I/O monad. And then we have hclose, which just given a handle returns I/O. So there's nothing like, strictly speaking, functional about like how we're going to do things here. That's what we're calling in system.io. The sort of terminology and the notion of having like a handle and a file pointer, that's just common to like all paradigms. So I'm just trying to emphasize that this is not something that's special about Haskell. We have everything that we've done from the previous lecture if we just prepend the word H here. And this is confusing and it irritates me because this is exactly the same agreement that we made for defining helper functions. But in this case, H means handle, right? So this is H get char is the handle get character. Right, so not getting it from standard in, but from getting it from a handle. And standard in is a handle, but this one is going to allow us to use like multiple handles. We can also handle put a character, given a handle and a character. I can give you a sequence of I/O actions. I can get a character the old way, which means that I handle get a character from standard in. And putting a character the old way was handle putting a character given the handle for standard in. So all programs operating, like running in Unix, should have access to standard in, standard out, and standard error, I believe. Was there one more? Or is that comprehensively them? Standard in, standard out, standard error. Those are the usual ones. I think there may be more, but they may be exotic. Does anyone know of anyone else? Standard in, standard out? Yeah, I'm not sure. Okay, so here are the basic I/O over handles. So you can put a string, like handle put a string. So given a handle and a string, I can give you an I/O action. Given a handle and a string, I can give you another I/O action. It's exactly similar to the one before, but it appends a new line character. We can get a line given a handle, which gives you an I/O container, like wrapping a string, and I can check for the end of a file. So H is end of file given a handle. I can tell you. So this is kind of strange because even you would think that if anything could be a pure function, this would be, right? But remember, I can't strip IO from stuff. So to ask if a handle is at end of file, it's a container containing a bool. It's like an IO action that tells you what the state is, but I can't just return true or false in this case. Haskell allows for the entire contents of a file to be returned as a single string. So this is actually pretty useful in Haskell. Why is this okay? Like what philosophy does Haskell operate on that like reading the contents, the whole contents of a file is fine? Yeah, it's lazy evaluation, right? The file can be infinite if you want. We can have infinite, we have lots of infinite structures. So the philosophy that Haskell is going to use is like, I can read the entire contents of this file. I don't care if it's terabytes long because I'm ever only going to give you access to like the next thing that you ask for. Right? I'm going to give that to you at the very last moment. So it's only reading what is necessary from the contents of the file. So something that would normally be a disaster, right, to read the whole contents of a file into your RAM, totally fine in the Haskell philosophy. Write a function that reads lines of integers from a file and writes the sum of each line to another file. Okay, you're going to have to help me with this one, or I may have to refer back. So let's go out to, okay, so we need to write a function that reads a line of integers from a file. So we have that, and writes the sum of each line to another file. Okay, so maybe that will be here. So let's try to do this. And what did I call it? I just put it in main. Okay, import system.io. Main is equal to, main has type an IO action. Okay, so what do I need to do something now? So what do I need to do? Yeah, I need to open a file, 2 files actually, one for reading, one for writing. Then I need to like read the numbers from one of the files. I could basically need to perform ADDIO on the file and then push it to the other one. Geez, I don't. Let's see. Okay, I'll keep going back and forth. So we need 2 handles, read handle and the write handle. And we'll figure these things out as we go. I just forget all of the names of the things. But in any case, we get a read handle, we get a write handle. And then I basically want to like perform ADDIO on the read handle, which is going to be something like, what do I want to do to the read handle? I want to sort of handle get, was it get line? Does anyone remember? Did I spell it right?
Yeah.
Okay. Handle get line, the read handle. And then I want to map words over this. And then I wanted to do something like let, okay, then I want to pull it out. Then I want to let y's equal the reading of x as an integer such that x gets drawn from x's. And then I want to put, or handle put, is it put line or put string?
Put string line.
Put string line like this?
Put stir line.
Stir line. And I want to put stir line show sum of y's. Oh, right. And this needs a handle, the right handle.
It also needs an int, right? Like what's y and what's string now?
This is going to be, this will be a list of ints. Isn't this fine?
No, like don't you put an int somewhere? Like what's
In?
yeah.
I'm not sure I follow.
The syntax of let, like it's always.
Oh, no. Yeah. No, this is a special syntactic sugar like within the monad. Right? I know it's. I wish they wouldn't recycle so many things because it does get, the syntactic sugar can get kind of confusing in Haskell. Yeah, but there's no, the in is implicit to like the monad itself. Like the in is in place. There are other ways of doing this. Like I can say y's, you know, return this and extract, like if you prefer that way, which is sort of more monadic, but I'm just going to go back to this way. Okay, so now all we have to do is, maybe I have to put brackets around that. So what are the invocations that are appropriate here? How do I get a read handle? Was it open file? Open file. Oh. Yeah, path, I'll just say the path is answer dot, no, this is reading, numbers dot dat. Pardon me? No, I think because I'm in the same directory, it should be fine. Where am I? Yeah, there's my foo, and there's my numbers.dat is here, yeah. So that's fine. And then where's the read handle go? Oh yeah, read mode. Write mode. Yeah, I don't use this monad very often. And then I want to maybe put it to answers.dat. Let's cross our fingers. Whoops. Hmm? Another apply. So that should put the string line to the right handle, and I'm showing. No, that should be fine. That should have worked. Go away. Go away. Okay, there's nothing there. I didn't close anything. Maybe that's the problem. Did I close in here? Yeah. Silly me. Good programmers close files. Close the read handle. And then close the write handle. Hmm? No. It seems like it should, right? But because it's in a do, like you would think that would work like what's the thing in Python? A with? Yeah. It's like I love that with is very handy. Okay, so let's try doing this. Okay, so there's nothing in answers. So let's see what happens when I invoke main. Yeah, maybe I'll close it and open it. Okay, so 111222555. Let's try main. Let's try looking at, what did I say, answer.dat. Oh, jeez. Ah, it worked. Oh, jeez. So let me just try doing it again, because I thought this thing can. Let's just put a few more numbers here.
Could we do another line? Like, could we make more than one line of?
Yeah, but then that, like, the way that we wrote our function presumes that all the numbers were inputted on one line.
Because it doesn't keep doing it. So
Well, we could call, like, get line again, or we could even like call it in a loop. But let's see. I just want to see if that answer.dat's going to change. Was it foo? Foo.
Is that a minus 24?
You should need a recompiler.
Oh, I didn't compile it in the first place. I'm like compiling it and reading it into the interactive mode. Did that change?
You need to call main.
But like, oh, right. It's run Haskell that I have to call. That's right. Run Haskell is like calling GHC, but it automatically invokes main. I think maybe that was the problem. Minus 24 now. Okay, let me put in like plus 100. Oh, no, just 100. And I'll do this again. 76. Cool. Okay, so we can now do I/O in Haskell, but yeah, you're gonna have to read over the notes because it's kind of strange, right? The philosophy here is that we can do I/O actions, but only from within an I/O structure. And if we want to manipulate anything being read by the user, or written by the user. Like I have to jump in the IO box and do everything I need to do with it, and then like jump out of the box. Right? So I can only ever pass around this sort of IO box to functions and stuff like that. But this is the reason, like you should be comfortable working with data types that like put structure over stuff, because this monad is the thing that immediately lets us pull out the structure. Now, I don't think there's a single question, there's no questions on your exam like that ask you about reading from files or anything like that. There is a question on your exam about IO, right? So you should know how to do, like the first half of this lecture, you should know how to work with. You can forget everything that I just taught you about file handling. That's just for completionist's sake. Do you know that you're allowed a crib sheet on your exam? Okay, so I hate forcing people to memorize stuff because I have like a really bad memory. So you are permitted a double-sided A4 crib sheet on your exam, if that makes you feel any better about like having to remember stuff. I got some pretty no flaps, I guess. And like don't print out like the entire contents of like people like literally had like the course slides, like all of them printed. Like one of the purposes of like having a crib sheet is it sort of like helps you prepare, right? So to like make the crib sheet, you sort of have to make an assessment about like what is important or not. There is also a cheat, like an API sheet on the back of the exam, which is identical to the one that I gave last year. So look at the exam from, for one, you have access to the exam last year, you should, through the library. So like give that a go. Like your exam's gonna be like just a touch harder, not maybe 10% harder. So keep that in mind. And yeah, we should start thinking about like now revising for the exam. So after this, I'm going to give you, we started marking A2, but NASA is super busy. So I can't release the grades until, I guess I can release the auto grader grades, but the handwritten stuff is gonna maybe not come out until next week because I'm waiting for NASA to do it. And then after this lecture, I'm gonna go back and just give the spec a quick read over, but effectively what I want you to do, so remember, like we're working with this polynomial data type on assignment 2. So what I want to do now, so there's 2 questions, and these questions, so I usually give you 3 programming questions. So the one I'm going to give you now counts as 2 of them, because it's one listing with like 2 things I want you to do. And the 2 things I want you to do is write an instance for show for polynomial, that polynomial data type, which you get brackets, the plus symbol, the caret symbol, and that's it. Right? This will be clear from the examples. So like I want you to like output stuff that looks like this maybe.
Yeah.
Something like that.
Mul as well. So are we
No mul. You don't get mul. You get left right bracket, caret, and x essentially. Right? We're just assuming all of the polynomials are going to be in x. I think I may have actually insisted on spaces. I'll have to check the spec. But anyways, given a polynomial, I want you to like write its string representation. And the thing that makes it difficult is that I don't want it to have redundant brackets. I only want it to have the brackets that it has to have. Okay, that's part 1 of the assignment. Part 2 is the opposite direction. I want you to write a parser, which is going to be able to take something that looks like this and read it back into the system as a polynomial data type. However, stuff that is being read back into the system can have like arbitrary amounts of redundant brackets. Like you're not only reading back the stuff that you've put out. Like this now is sort of like a user is typing in this polynomial into your system. So that's part 2. Like so you should be able to like accommodate stuff like this. Like I know it looks silly, right? But you should be able to, to read something like this properly. So those are the two parts. And so next week we're going to do parsers, which is like the totally new topic. I'm a little bit hesitant about it because, do you guys know what grammars are? Well, yeah, you guys would know, but what about the rest of you? No? So I'm going to have to give you sort of like a crash course in grammars. So I'm going to teach you how to like parse expressions like this. And maybe you can think about this. Like if I said, here's like an expression, can you like evaluate it for me? Like I give you like the string version of this, and I want you to give me back 17. Like how would you do that? Right? It's more complicated than you may think, like especially once you start putting in brackets and stuff like that. So next lecture, we're going to build a parser for reading arithmetic expressions like this, like including brackets. And then my hope is that you will be able to just make one little pivot. Like take everything that we've done for parsing like arithmetic expressions, make minor changes to like get a parser for reading polynomials, because they should be very similar. But in the end, you should appreciate what we've done, right? We've worked with a polynomial data type. You've defined like how to do arithmetic over that data type. And soon you'll be able to like display human readable versions of that data type and input human readable versions of that data type. So essentially you have like the basic components of like a computer algebra system, right? Like inputting polynomials, like doing arithmetic on them, taking the derivatives, outputting polynomials. In fact, I'm looking for someone, if someone wants to do like an honors project, I want to write like a pretty printer for this type of stuff. Do you know what I mean by that? Let's see, do I have Maple on this? Yes. So like I want to be able to duplicate this type of functionality. So I want to build that pretty printer in Haskell. So if someone wants to do a project, there's a bunch of projects now that I want to do. So I want to extend the polynomial, that example to do factoring. Right? Given a polynomial, factor it into irreducible components. That would be an interesting project. I want a project where we accomplish getting things printed like this. And like this is actually quite robust. Integrate that last thing by x. Oh no, it actually did it. Let's do something more complicated. All right. Well, this is the programming language that I'm an expert in. Like I worked for this company for like the entire duration of my graduate degree. So it can like, yeah, it's called a pretty printer. This is giving us formatted 2D representations of stuff, which I think is pretty cool. And I've never managed to figure out how they did it, but it seems like within the capacity of an undergraduate student to figure out how this is done. So if you're interested in doing any of these honors projects, just come give me a talk. I think if you're an engineering student, that goes a lot better. Like students from ITEE, students from math, I'm not even sure I'm allowed to work with you. So we'll see. Okay, so expect that. That will be the last assignment. And then I also want you to think about revision and stuff like that. And I'll start releasing some of the solutions for your homework so you can use that to study as well. But certainly get the exam from last year and ask yourself how much of it you'd be able to do. Okay, so yeah, it's a tough lecture. Let's just reflect on it a little bit, but just remember everything's in a box. And you got to get in the box to do I/O. All right, so I'll see you guys next week for parsing. Thank you. Bye, chat. They'll be back. Brawly. That's the new terminology I've learned.
This is